Representations of reactions. So this is about drawing the particle model diagrams. Okay? So, alright, so same enduring understanding about chemical reactions and equations, but here you can represent given chemical reaction or physical process with a consistent particulate model. So, basically, we use these a lot, chemists do, to represent reactions as a way to visualize the changes as they take place as the atoms rearrange. So for one example here, this one, as you've seen in various forms in other sets of the notes as well, has showing the ions. It's basically like kind of grayed out the water molecules because there's so many of them. But it's really showing you the ions here. So the K plus in this one, the I minus, okay? The purple's the I minus, the gray is the K plus, the potassium iodide. And then in the second circle, the other solution, we have the lead and we have the nitrates floating around in there. The lead is the yellow circle. The nitrate, of course, is the red with the blue in there. And it's showing how that's going to combine for a precipitation reaction. Now on the macro level, we see the yellow precipitate, okay, it's bright yellow. But on the micro level, showing it, you know, or I'd say on the atomic level here, showing how the lattice crystal is going to build, and it's in a repeating pattern of positive, negative, because opposites attract here. But as you can see, the only thing left over in the chamber are the potassiums and the nitrates floating around because they're spectators. So we have this one example here we've seen a few times now because we've been talking about precipitation reactions in detail. But we need to be able to represent all matter on that level in that, looking at those diagrams. And that's why you see them a lot in the problem sets as well, because they use these all the time. So one thing to think about too, starting off with what's the criteria, what do we need to care about, important parts of the representation. Relative location, and that usually has to do with the phases of the matter or the states of the matter. Solid particles should be close contact in order that maximizes attractions and minimizes repulsions. One other thing that you should notice about the way that the solid is being represented, especially in this particular one, it's like sitting in the middle of the container because it has its own definite shape. It doesn't take the shape of the container. So it's just in the middle, sitting there because it's holding its fixed position, has those stronger forces holding the particles together. So it doesn't actually like fill the container at all. It just kind of sits at the bottom, okay? Now the liquid here, the liquid takes the shape of the container, but it's definitely going to show more randomness in the arrangement. And the particles are still closely packed together. But yes, they touch the sides of the container because, you know, it fills the shape or takes the shape of the container. And then of course over here the gas should be randomly dispersed throughout the container because gases are in constant random motion. They spread out. They fill the container completely. So you would see that these different arrangements for the different phases of matter. All right, so I also put this diagram in here because it shows you the little red particles being held together by the red forces. And as you can see, once again in this top one, kind of sits in the middle of the container because the solid has its own shape. It does not do anything with the container. It just sits in the middle of the container. Here the liquid, you can see a bunch of the forces. And remember, liquids have IMFs, but because they're flowing and flipping and sliding past each other, there are times when they have the attractive force, and then there's times when they have some repulsive forces as they're flipping and moving. But definitely weaker attractive forces here holding that liquid together. Solid, of course, has the strongest of the forces of the phases. And then for the gases, where they're in constant random motion filling the container completely, we make the assumption that they don't have any forces holding together. They are in constant random motion, perfect elastic collisions going on, okay? Bounce off the container, bounce off another particle, no attractive, no repulsive force there. All right, so aqueous solutions. A couple other things to note about aqueous solutions. kind of looked at the precipitation reaction in the first slide there, but here, there's also a couple other things we need to consider. Sometimes it only shows the solid particles like in the previous diagram. But ions should always be dissociated if they're soluble, so that includes like breaking them apart and giving them their charge. Okay? Solvent water particles, when included, should be oriented with the dipoles in the correct direction to maximize attractions and minimize repulsions with the solvent and solute particles. So that would be like one right down here, this type of picture, okay? This is the dissolution of sodium chloride, right? So, if they're asking you to look at how the waters are oriented, you see the chloride here is a full -1 charge. So the hydrogen side of the water, which is the partial positives, they face inward towards and attract to the negative on the chloride. Opposite is true down here when we have a sodium. In the case of the sodium, which is the plus and a plus, that means the oxygens are facing inward because they're the partial negative side. They are attracted to that full +1 charge. And that is actually, this right here between them would be the ion dipole force. You have the ion, and then the dipole force is coming from the water. So that is one of those like in-between forces. It's definitely, I would say, stronger than like H bonding, dipole-dipole London dispersion, the intermolecular forces. But is, you know, kind of in between with those intra forces like ionic bonds and covalent bonds and metallic bonds. So that's one thing you might see, and I've seen this multiple times on free response questions in past exams, recent past exams in the last 10 years, just so you know. So this is definitely something we will practice multiple times. Now the other thing was like the precipitation reaction, similar to the one that was in the front, but if you're drawing it, this would be more of like a representation of you drawing it rather than the perfect one that comes out of the textbook. So here we have our NaOH in this beaker, the magnesium chloride in that beaker, and they're showing the dissociation. If there's two of them here, they're not telling you how much you're starting with. They represented it by putting 2 sodiums and 2 hydroxides in there, and then the magnesium chloride is 1 formula unit. So you have the 1 magnesium and then the 2 chlorides, because this breaks apart into 1 magnesium, 2 chloride ions. Over here though, you see the NaCl stays aqueous. You see all of them still separated because they're spectator ions, but the magnesium hydroxide, that's all made at the bottom here looking like a precipitate that has fallen to the bottom. Okay, and so you draw it kind of like that. Couple of other things. There are other context clues to consider. One of the context clues, the surface or the interstices of an alloy. Now, we will go into detail in discussing what alloys look like later on, but alloys are usually represented by this type of picture. This is a variation of different alloys. Alloys are metal mixtures, okay? Like brass and bronze and sterling silver and some of these other things. But they usually represent the alloys with just circle pictures. And they don't put charges on them because it's really not like charges that are involved here. It's more of the sea of electrons with the metals. They do those delocalized metallic bonds. So they represent them with just regular atoms, circles, but they do color them differently so that you can represent and understand that, like this blue one right here is a different metal than the green one, which is a different metal than the white one. But you can have lots of different metals in an alloy. The other one shows you, like, some of them have these little atoms that fit in between, like steel is one of those examples. It's mainly iron, but it has the carbon in between because they're smaller and they fit inside the little gaps. But we'll go over alloys in details, but that's one of the context clues. Precipitate at the bottom, of course, we've looked at a couple of those. You see the solid that fell at the bottom. Now, interfaces where there are two different substances meet. We've done a few of these, not many, but this picture over here, the platinum catalyst surface, is mainly showing you that, because this bottom one with the purple circles, that's the solid, it's at the bottom. And then you have oxygen and carbon monoxide gases that are coming down and reacting with it. So it's showing you that you have a gas layer and you have a solid layer there. So you might see something like that. So if you have, something that's sitting at the bottom, not taking the shape of the container, you would know it's a solid. And then if you have stuff on top floating around that, obviously it would be a gas. All right, so a couple of other things. Amount. Proper number of atoms of each element when given a formula, or a concentration, or the number of moles. Like in the ones of the problem set where you had to count the little circles of stuff, figure out how much it could make. So they definitely have to go by their amounts because we have limiting and excess now. Some things may not get completely used. You also have to represent that. And that is by using the law of conservation of mass. So you have two reactants to start with. One of them runs out, but that means the excess one should also still appear at the end because we don't destroy matter. You have to conserve it and represent it that way. So if we're looking here at this lovely diagram here, this one is the AgNO3. I don't know if you can see it because it's kind of small. So you have your Ag pluses. These are your Ag pluses. Circles. These are the NO3s right here. That's the NO3 minus. Didn't really draw that well here. Let's do that again. NO3 minus, NO3 minus. Now this is telling me this is 0.1 molar. Now there's two of them in there for 0.1 molar. Okay. And over here, this is the NaCl. This is 0.2 molar. Now, here are the NAs, 1, 2, 3, 4. So basically, if it's 0.2 molar, it's double of the 0.1, where these Ags only have 2. The NAs over here, if it's 0.2, has 4. So it's doubled, represented that way. These are the chlorides if you can't see them very well. Drawing them back in here. Now, when these things do react, we do know that the Ag, based on solubility rules, is going to form a precipitate with the Cl. So we're going to have that precipitate out, and that's what they're representing here at the bottom. This is Ag, Ag, and the Cls. These are the Cls. And as you can see, they wrote the charges in there because these are ions, but they also have them alternating because the positive attracts the negative, and so forth. So they arrange them to maximize attractive forces, right? Maximizing attractive forces. The sodium and the nitrate are spectating. So you should find all of those up here. You should have 2 of the nitrates, which we do. We have 2 of the nitrates. And then we should have 4 of the NAs, which we do. Now, those other 2 things, because out of here we used both of these silvers, but we only used 2 of the chlorides. So that means 2 of the chlorides are left over. So that's where you see the extra 2 chlorides there. They are in excess. The silver is the limiting, the chloride is the excess. So you have to do kind of a lot of counting there to make sure it's being represented correctly. But also when you're building the crystal lattice of an ionic compound, make sure you alternate the charged particles because the positive attracts the negative and so forth. All right, so a lot of times too, this is a saving grace. They give you a key to work off of. So you don't have to invent your own shapes. Sometimes you do, but sometimes you don't. Okay? So use distinct shapes, symbols, colors, shades of them, or use the key here. This is one from College Board. So you see they're using the little white circle for H, the bigger white circle for O, and the bigger dark circle for F or fluoride, F minus. Okay? So we'll get into more of the showing the partial charges when we get to dipole moments, and more about when we draw the molecules and get into polarity. But I've already shown you partial charges. We use the lowercase delta, partial positive, partial negative. You see that next to anything on a molecule, you should recognize it as being a partial charge. If you just see a charge like Na+, that's a full charge. Full charges, of course, stronger than partial charges. Okay? So that kind of goes back into like maximizing attractions, aligning them appropriately. You would flip the dipole to face the correct orientation. Now it says use appropriate sizing, which we'll get into more about the size later because that's a periodic trend. Does anybody remember how atoms in terms of size work? If you go up and to the right, the atoms get what?
Bigger.
They get smaller.
Oh.
Yes, as you go left and down, they get bigger.
Yeah.
But we will go back over periodic trends in detail, so not to worry. And like I said, a lot of times they give you the key anyway, so you can use their appropriate sizes. All right? But yes, trends will be retaught later on. All right, so for example, I gave you 7 examples of different drawings where sometimes they draw it for you and you interpret. Sometimes you have to draw it on your own. So let's start. Go ahead, give you like 3-4 minutes. Look at example 1. Use the context clues to try to figure them out. Okay? And we will come back and discuss the answers in a moment. Looking up here, what are the formula for the reactants? They gave you the key over here. We have the darker ones H, the light ones are Br. So if you see here, they are written together, bonded together, so these ones are going to be diatomic. So you should have seen H2 and Br2 are your reactants there, just based off of the context clues from the key. Now, the only thing also shown here that could possibly be the product is where they're showing you that one of the dark is bonded to one of the white, and therefore that means it has to be HBr is your product. Now, I know that we spend a lot of time in Chem 1 telling you anything with an H in the front is always an acid. Well, sometimes these compounds like HBr can be gases, and they do float around. And yes, you can bubble them through solution and they will act as an acid in that fashion when they're bubbled through, but they don't always have to be an aqueous solution, okay? So what is the balanced equation? Well, you would do your H2 plus Br2 gives you HBr, and then you would have to balance it with a 2 in front of the HBr. Now notice it says include phases of matter, so I'm using the context clues for that. As you can see in all of the boxes, although they are small, all of the molecules are spread out and filling it completely. So you would make the assumption that everything in there is a gas. Now, what is the main difference between picture 2 and picture 3? Anybody get that one?
More reacted. Yes.
More reacted. You got more produced in picture 3 than you did in picture 2. So more HBr has formed. Picture 2 only had 4. Whereas picture 3 had 6. That was your main difference, that more had formed in 3. Now, if you look at any of the particular pictures, doesn't matter which one. Yes, this is an equilibrium system, and we'll go into detail what equilibrium is later. But if you're looking just at each picture, what do you notice about the total atoms of each element?
Law of the conservation.
If you counted them, they're going to be
The same.
the same. So we are conserving. Yes, following the law of conservation of mass. And that would be what you would see here represented by this set of diagrams.